And Syncardia, just to give you a little bit of background on Syncardia, who we are, and the qualifications for being able to make a presentation like this is Syncardia is the only FDA-approved total artificial heart that is commercially available. And we have been FDA approved as an implant, as an artificial heart, since 2004. And the artificial heart, we've implanted more than well over 2,000 people as a bridge to transplant. So it is a technology, and you can look up on your own a little bit about Syncardia and how we have solved some of the problems that we will discuss later with the artificial heart. About half of our patients that have been implanted have been in North America, and about half of them in Europe. And we've had several also in Australia. The technology, even though we have the FDA approval since 2004, this technology is actually in its infancy. It is extremely challenging to pump blood. And we congratulate all of you on joining this global effort, because it is not an easy problem to overcome. But I'll tell you one thing, it is so gratifying to see a person who is in such extreme circumstances with their health, and to see them again be able to survive and go on and live and thrive and be with their own family. So it is a very, very worthy effort. So my objective today is to cover a basic anatomical overview of the circulatory system. And by my background, I am an electrical engineer with an emphasis in biomedical engineering, and I have a pre-med background. So I was able to, one of those few individuals who had the opportunity to marry my love and passion for engineering and electronics with my passion for the anatomical and physiological conditions to overcome those as a biomedical engineer. So when we talk about the basic anatomical overview, my terminology will be probably more like an engineer than an anatomy professor. And we will have plenty of time at the conclusion of the slides to talk about the questions. So please note your questions as we go through these, and then we will have ample time at the end to answer your questions. So I do not know your individual backgrounds and how much anatomy or physiology you may have had, but basically the cardiovascular system is a network of blood vessels, and these vessels take blood to every single cell in your body. By the way, a normal human body has about 1 trillion cells. It's hard to imagine 1 trillion. That's like 10 to the 14th power. So this network of vessels that goes throughout the body provides the nourishment that these cells need. It goes to every cell in the body, and the heart is the organ that propels the blood through this network of tubes throughout the body. Now, we're going to talk a little bit about some of the nomenclature. These vessels, we have veins and arteries. Veins are depicted usually with a blue color, and the veins carry the blood to the pump, to the heart. The arteries are the veins that carry the blood away from the heart, and that is usually depicted by a red color. So the veins are not actually blue and red, but the blood that circulates through them is much darker on the veins that comes back to the heart, and much brighter red as it goes away from the heart. We'll talk a little bit about why that color change in just a moment. So we're going to trace the flow now through this amazing pump. By the way, just for a frame of reference, your heart, your healthy heart pumps about 100,000 times every day. And in a lifetime, it's about 35, well, in 1 year, it's at 35 to 40 million beats every year. And during a typical lifetime, this amazing pump will pump about 2.5 billion times that it will contract. It's an amazing, amazing muscle. Okay. So as we trace the blood through, we're going to take a look at the blood flow as it comes to the heart. The blood comes to the heart through two large veins. The upper vein is called the superior vena cava, and the lower vein is called the inferior vena cava. Where those two blood vessels meet, that is the beginning of your heart. So those two blood vessels join together in the upper chamber of the heart that is called the right atrium. This blood is then, the atrium will then kind of punch down a little bit, push the blood through the tricuspid valve into the right ventricle, and then the right ventricle will pump it up to the pulmonary artery. The pulmonary artery, it goes to the lungs. And the pulmonary artery, if you look at the right ventricle, it pumps blood up, and the pulmonary artery branches out to the right and to the left. And those are the main vessels that go to your lungs. And when the blood goes into the lungs, I have an amazing thing that happens. It goes to these little tiny vessels that are so small that the blood cells virtually line up in single file. That's how small these blood vessels are in your lungs. And that is where the blood changes color. And as you get into this, if you're able to go and as you start actually pumping blood, you'll see that the blood coming into the lungs, coming out of the right ventricle, is very dark in color. It gives off the CO2, and the uptake is oxygen that attaches to the hemoglobin in the blood, and it turns that bright, bright red. And again, that is why we have this blue and the red color. All right, let's continue on. After the blood is oxygenated and comes back to the heart, it comes from two pulmonary veins on the left and two pulmonary veins on the right into the left atrium. So the left atrium is the collection chamber where the blood is returning to the heart. That left atrium will pulse down and push the blood gently into the left ventricle. And then the left ventricle will pump the blood up into the aorta. And you can see the shape of the aorta has that. It goes up and it arches over. That's called the aortic arch. And those three vessels that come out of the top of the aorta supply blood to your arms and to your head. And then as the aorta goes down through the thorax, down into the central part of your body, it branches off to all of the major organs. And that's the bright red blood that is carrying the oxygen to the different areas. So the valves inside your heart, you can see that the valves is what creates the unidirectional flow through the heart. In a little bit later, we're going to talk about the volume of blood that is pumped on the right and the left. So that's a whole other discussion. All right. So as I stated before, the right and the left atrium will push down. They kind of contract, the muscles contract and push blood into the ventricles, and the ventricles push the blood out. By the way, the left ventricle does about 85% of all of the work in the heart. So that's a very, very large percentage of the total workload. And as engineers, we talk a lot about work and energy. The main energy is from the left ventricle because it has to pump blood all the way up to your brain and all the way down to your toes and have enough pressure to return it back from the extremities through the superior and inferior vena cava back to the right side of the heart. So the blood, as it comes out of the heart, the left ventricle, again, does about 85% of the work. And that left ventricle is going to push the blood up in the aorta. And when it contracts and the blood is ejected through the aortic valve, the pressure rises to a fairly good pressure head. And then as the left ventricle relaxes and starts to fill again, that aortic valve closes and the pressure in the aorta drops down and goes lower and lower. And just for nomenclature, the pressure as it goes high, the highest pressure is known as the systolic pressure. And when it drops down, the lowest pressure is the diastolic pressure. And you all have gone to see gone to have a physical where they measure your blood pressure, and there will be two numbers. And there are a lot of things that you can tell by the pressure of your blood about the health of your heart. So you'll have a high and a low pressure. That's the systolic and diastolic pressures. You can actually feel the pulse in your body. One of the very well-known places is the radial artery in your wrist. If you turn your hand upward with the thumb pointing away, then you can put two fingers on that outer side and you can feel your pulse. And you can see with the sign here, there are many other places in your body that the pulse is commonly felt. We're going to talk a little bit later about pulse and pulsing of blood, and if it is necessary, we'll have a little discussion about that as we talk about pumping blood later. One of the other things that is sometimes ignored is the blood in the veins as it's coming back to the heart. Your veins actually do have valves in them that help it so that the blood does not pool down, especially in your lower extremities. There are little valves that keep the blood going in the right direction. So that is basically the healthy heart and all of the good things about a healthy heart. However, there are times and diseases where the heart muscle cannot pump efficiently any longer. Sometimes the heart muscles become stretched out, non-contractile, and they become very, very big. The muscles stretch out, and that is known as cardiomyopathy. The heart becomes weaker and weaker. The blood pressure is not able to regulate anymore. And there's a lot of discussion that can be had around cardiovascular diseases. But basically, cardiomyopathy is the general term that is used for a failing heart. And you can have a restrictive cardiomyopathy, congestive, or idiopathic cardiomyopathy. There are other conditions that can also affect your heart and prevent it from pumping this vital blood. But basically, if you do not have enough blood, then your other organs tend to start to fail. You can have damage to your brain, your kidney, liver, lungs, and gastrointestinal. And so all of these organs need to have this blood flow, and it needs to be delivered with the pressures and the flow that are necessary for the health of all of these major organs. Now, if you have a biventricular heart failure, the the gold standard for curing this or for solving this problem, if you have a heart that is failing, is a heart transplant. That is where you take another person's heart who has died tragically from some other ailment or some other form. They've died, but their heart is still good and healthy. And you actually cut, you can see on the picture here, where you have the purple veins over on the left-hand side. That's the superior and inferior vena cava. They cut that chamber open, the right atrium, and you can see the 4 vessels coming into the left atrium, those 4 right in the very middle of that diagram. And then the aorta and the pulmonary arteries are excised, and they take another human heart and sew to those places and replace the heart. It's an amazing, amazing thing to take a person whose heart is failing, put another person's heart in there, and have them turn from gray to pink. It's an amazing thing. That is the gold standard, and it is very, very well documented. We know how to prevent rejection from another person's heart being placed into your body. And the problem is there are a lot of people who could benefit from a heart transplant. They're otherwise healthy, but their heart is diseased. They could be helped, but there is a shortage of donor hearts that are available. Globally, there's probably about half as many heart transplants that are done that could be done if we had an alternative. So that's what we're here. That's why we are here, is we need to ask ourselves, can we design a replacement for a heart? Could we actually make a total artificial heart? It is not as trivial as you might think. We can design a lot of wonderful pumps, but there are a lot of very unique things to pumping blood that need to come into our discussion. And that is a little bit of what we're going to discuss next. Some of the things that we need to consider as engineers is the blood pressure. The pressure coming into your pump that you will be designing has a relatively low inflow pressure. If we try to keep the blood pressures in the range where normal physiology is, our inflow pressure to your pump is going to be around 5 to maybe 12 millimeters of mercury. It's a fairly low pressure coming through the superior and inferior vena cava. The outflow pressure, you need to have enough pressure to develop pressure to go to the lungs of about 30 to 50 millimeters, and to pump out of the aorta to provide enough power to go to the brain and to the toes, you need to have a systolic pressure of around 110 to 140 millimeters of mercury. That's what normal physiological pressures are. And you have to also realize that this pressure, the outflow resistance, is variable. Sometimes people get anxious or angry or sad, and those emotions can actually change the blood pressure. So your pump will have to be able to respond to various pressures. Not only do your blood pressures change, but the volume coming to your heart changes. You need to make sure that your pump will have enough output to provide enough nourishment to all of those 1 trillion cells in the body. You've got to make sure there's enough volume in liters per minute. You've got to be able to put your pump to help big people and small people, and you need to have variability in your blood volume. For instance, one of the things that we have found with our patients with the artificial heart is if they go to their local convenience store and get a super large soda or something and they drink that, their blood volume will go up. It takes a while for the kidneys to come and clear that extra fluid. So you need to have your pump be able to respond to various pressures and various blood volumes. Now, ongoing about what we need to worry about as engineers. Blood can actually be described as another major organ of your body. And there are cells that flow within your body, within your blood. And we talked a little bit today about the red blood cells, and that is the largest number of cells in your body or in your blood. And the red blood cells are only one component of a very complex fluid. And it is very sensitive. Those cells are very sensitive to shear stress. So you've got to make sure that your pump will not damage the blood cells by shear stress. Also, the change, if you have a pulsatile pump, you need to make sure that your change in pressure over time is not too high. We discovered early on in our research at the University of Utah that when we made our first versions of the pneumatic artificial heart, that by having a very high dPdT, we could actually damage the blood cells with the valves that were in our original artificial heart. Of course, in that early stages, in the early research, of course, the blood direction is critical. So we had valves. But we need to ask ourselves, what if we have a rotary pump, a centrifugal pump, or an axial flow type pump? Is a pulse really needed? Do we need to have a pulsatile flow? I'm not going to fully answer that question because there are still many debates about whether a pulse is needed. But as an engineer, I just make one observation of all of the different pumps that have been designed with ventricular assist devices and with other artificial heart technologies that are being designed and under development. Those who have had a continual flow, one of the things that they're all working on now is to how to incorporate a pulse into their devices that are pumping blood. So it appears that there are some portions of our anatomy and our physiology that possibly a pulse may be important, perhaps in our gastrointestinal tract, perhaps in our kidneys, in our liver, for those organs to do their job. Sometimes, again, the jury is out, and some people do very, very well with a continual flow left ventricular assist device. Others feel like a pulse is necessary. So I'll just leave it at that because, again, the jury is still out on how essential a pulse is. Now, the blood material. I mentioned already that blood is a very complex thing to pump. There are platelets that circulate. When we have a cut to our skin and blood is coming out, the platelets will cause a clot. This is very important. We have to have clotting. It is very important for us to be able to clot. However, if you use the wrong type of material, the clot can happen spontaneously just by touching the device, and you will have clotting that can happen, and you can have clots inside of your pump. And it seems kind of obvious, but you need to make sure that the material that your pump is made out of is not toxic. There are some wonderful materials that are very good and durable, long-lasting. However, they're toxic when they are in the human body. And Also, you need to make sure that the materials you use are non-carcinogenic. You don't want to have someone, you solve their problem of having blood flow and then have them develop a cancer that is directly attributable to the material that you used in your pump. By the way, when we're talking about toxicity and carcinogenicity, those are questions that you will need to answer to the regulatory bodies. The European, Australian, Canadian, and US regulatory bodies all will ask for those types of testing on your materials that you select for your pump. Now, I told you earlier at the very beginning that we were going to talk a little bit about the right and the left flow. It seems almost intuitive that you have blood coming from the superior vena cava and inferior vena cava, and that's all the blood coming back to your heart, and it pumps it to the lungs, and then it comes from your lungs back to your left ventricle. And so you would think that the left side of your heart pumps the same volume as the right side of your heart. You would think that, but it's not so. One of the things that has been a challenge for people making blood pumps, when you replace the right side circulatory system and the left side circulatory system, the right and the left flows are not the same. Why is that? That's a very, very curious fact. And me as an engineer, that's one of the things that I had a hard time understanding at first. Why can't my right ventricle and left ventricle pump the same volume? Basically, the answer is that when your left ventricle squishes down and you push all the blood out of that left heart, that left ventricle, that blood is going to nourish all of the cells in your body. And some of that blood that's going out to nourish all of the cells in the body, some of that blood is going to be nourishing the cells in your lungs. And so the blood flow will go to your lungs, and part of that went to nourish your lungs will actually leak back and come back to the left ventricle. So your left ventricle actually pumps more than your right ventricle, but not always. And that's the challenge. Some people, the amount of blood that the right heart pumps and the left heart pumps is exactly the same. But in other individuals, it can be as much as 10% more that is pumped from the left ventricle, but not always. So that's the challenge. The right and the left have to have a balance of flow. And this has been achieved from some pumps by having a variable volume that can shift periodically to help balance the right and the left flow. Okay, so those are some of the very, very interesting aspects of pumping blood. And now, the 800-pound gorilla. First of all, durability. I know of a group that recently developed a fantastic 3D printed tissue heart. It was amazing. And the data showed that they had done a 3D printing of heart tissue that actually contracted. And I thought, wahoo, this is wonderful technology. The only problem is the tissue in the heart that they 3D printed would only operate for a few hours. I would not want to have an artificial heart that only lasted for a few hours. We need to have long-term durability. This is a big challenge. Again, our heart pumps around 40 million times. It beats 40 million times a year. So durability is very, very important. The other thing is, will it fit? I know of one group who developed an artificial heart. Technologically, it was amazing and so elegant from an engineer's standpoint. I marveled at the design. It handled the right and the left differences in the balance and all of that. But it was so large that they could never put it into a person and have it be for normal sized people. It could only go in great big people. Also, you need to consider, how do you connect the artificial heart into the human anatomy? Currently, most people who have been developing artificial hearts connect to the right and the left atrium. Seems like a logical place to put it, to take where the blood is coming back to the central part in your chest and hooking it to the right and left atrium. But since we're talking about heart hackathons, we don't know. Maybe one of you will come up with a very good, clever way to attach a heart that is not necessarily in the physically available space of a diseased heart. I don't know. We will see. The other thing is, how do you power this? Right now, the Syncardia artificial heart, which works very, very well, and for years if needed, it is a bridge to transplant. And what we're trying to develop here is a permanent total artificial heart, one that can go in for a long time, but we need to know, how can we power it? The Syncardia artificial heart uses air or pneumatic power. So we have tubes that come in, and they come in just under your rib cage, and they go in through the body. So you have a skin interface. We have to make sure, how are you going to get power into the body? There have been some people who have been looking at other technologies, implantable batteries, but then how do you recharge those batteries? Can you do some sort of a charging through the skin that doesn't excite the skin into creating scar tissue and create too much thermal effects? So again, those are all engineering problems that we have to figure out how to fix those challenges as an engineer. So with all of these things to consider, we'd like to just wish all of you the very, very best on your endeavor, and look forward to seeing your designs and your innovations and all of the clever things that you come up with. And with that, I will go ahead and stop sharing my screen. I'd be happy to answer some questions if you have.